Today we are going to discuss about the dipolar polarizability, or rather the orientational polarizability, most famously known. It is important only in materials which contain the complex ions having permanent dipole moments. So, in the absence of an electric applied electric field, the polar molecules are randomly oriented such that the net dipole moment within any small volume is zero. So, in the presence of an applied electric field, the dipoles tend to align themselves with the applied electric field. So, let me go into the slides. So, this is the basic phenomena of orientational polarizability. The net effect is that each polar molecule is a small charge dipole which aligns with the applied electric field and influences the total electric field both inside and outside the material. And the total polarization of a given material may arise from a combination of electronic, ionic, and orientational polarizability. Uh, so, these dipoles are not free to rotate in the solid, which they do so in the liquid or gas phase. So, an applied electric field is applied electric field helps orient these dipoles along the direction of the field. Such an orientation is opposed by the thermal agitation, which tends to randomize the dipoles. So it is because of this reason the calculation of dipolar polarizability has to be made under thermal equilibrium. So now let us suppose that a dipolar system is placed in a uniform electric field. So this is techniques how our polar substances, in absence of the external field, these when a material is placed in an external field, the dipoles rotate about their axis of symmetry and align with the application of the field. And this is the randomized dipoles, and this is all aligned in the direction of the electric field. So naturally, this P is proportional to E, and this proportionality constant is the ionic polarizability. So these are the few examples of asymmetrical molecules like H2 or HCl, which possess the permanent dipole moment. And in the randomized state, this average of the dipole moment gets zero, and when placed in the electric field, tries to align the dipole moment along the direction of the field. That's why this P average is not equals to zero. So a dipole such as HCl placed in a field experiences a torque that tries to rotate it uh, to align this P naught with the electric field. So in terms of molecule, it is also important as it is very predominant in case of liquid crystals and polymer type of materials where the molecules are tries to get aligned with the applied electric field. So when electric field is placed in the dielectric material, it tries to align the dipole in its direction. That results in the existence of the dipole moment in the material, and basically it occurs in the asymmetric molecules, and also in the dependence of the temperature, as we discuss later on. So where mu is the permanent dipole moment. So this is the basic derivation of how a dipolar system is get perturbed by the applied electric field, out of which we consider a dipole as shown in the figure. So force exerted by the field on the positive and the negative charges, the dipole is equal but acts in opposite directions, right? Thus, a torque exerted by the field on the dipole having a dipole moment P is given by this tau is equals to P cross E, where the magnitude of the torque is P E sine theta. The theta is the angle between the direction of the field and the moment, and the direction of the torque is such that it tends to turn the dipole into the direction of the field, that is to reduce theta. The potential energy of the dipole is the field is given by u is equals to minus p dot e, that is minus p e cos theta. So it is very much evident that the energy of the dipole is minimum, that is minus p, when theta equals to 0, that is the dipole is aligned parallel to the field, and it becomes maximum, which is equal to plus p, when this cos theta becomes minus 1, that is theta equals to pi, that is when the dipole is anti-parallel to the field. Thus the potential energy is a function of angle despite the minimum energy conditions, that is theta equals to 0, right? All the dipoles do not point in the direction of the field because of thermal agitation. A dipole of moment P making an angle theta with the direction of the field contributes to the polarization component P cos theta, that is Px, which is the x component of dipole moment. So according to the Boltzmann statistics, the probability of finding a dipole within a solid angle theta to theta plus d theta, right? That is abbreviated most popularly known as d omega, is proportional to the Boltzmann factor e to the power minus e upon kt, that is f theta equals to exponential minus u is the potential energy over kt, k is the Boltzmann constant, and it finally turns out exponential pe cos theta by kt, right? So this is how we average the moment contribution per dipole P lying within the solid angle can be determined by integrating over all angles from parallel alignment, that is theta equals to 0, to the anti-parallel alignment, that is theta equals to pi. So the my P average would become the average of, that is 0 to pi px f theta d omega times 0 to pi f theta d omega, where px is the p cos theta and d omega is the solid angle 2 pi sin theta d theta, and f theta is the Boltzmann distribution. So substituting these values, this equation becomes like this, that is 0 to pi p cos theta 2 pi sin theta d theta, and exponential p cos theta upon kt over the same thing except this p cos theta, right? Then we substitute a is equals to pe upon kt and t equals to cos theta, that means dt equals to minus sin theta d theta, and this equation is simplified as this p comes out of the integral, as this is the integration over dt, so 0 minus 1 to 1 exponential ta t dt upon exponential ta dt. So this is a particular trick of integrating without integrating by parts. This our uh, numerator is nothing but the differential of the denominator. Therefore this trick has been applied, dd of log exponential ta, and finally it turns out by like this, log e to the power a minus e to the power minus a, and this is a particular function of cot hyperbolic a, and this is p cot hyperbolic a minus 1 upon a, that is PLA. This LA is a particular function called the Langevin function, because Langevin first derived this formula in case of paramagnetic gases, but Debye applied this relation to an applied dipole gas, electric dipole gas. So let me see the figure. This is the figure of the a upon a is equals to mu upon kt upon the Langevin function, where a is very large, and this shows the plot of the Langevin function LA as a function of a, where a is very large. That is, when a is large, a is p upon kt. That is either when e is large or when t is low, right? Or at high field strength or low temperature, this function approaches the saturation value unity like this. So this corresponds to the maximum alignment of the dipoles along the direction of the field. So for small values of A, that is when E is less and T is high, the dipoles along the direction in the small values, we have cot hyperbolic A is 1 upon a plus 1 a by 3 plus a cube by 45, and neglecting the higher order terms, the most significant term is a by 3. So actually, in order to approach the value of a to be unity at room temperature, the field strength of about 10 to the power 9 volt per meter is required. So thus for a moderate field such as this one, so this is required. So such a moderate field such as 10 to the power 5 to 10 to the power 6 volt per meter, the moderate temperature 300 K, the value of A is on the order of 10 to the power, only 10 to the power minus 3 to 10 to the power minus 4, which is much less than unity, and hence the above equation um, could be used safely using losing much of the accuracy. So this assumption may be justified by showing that the magnitude of kT at room temperature is many times larger than the potential energy gain resulting from the alignment of the dipoles at the same temperature. So moreover, the value of A found in the most experimental situations in the same order, but substituting the value of LA as A by 3 and replacing this in the Langevin equation, we get P average is nothing but P square upon 3 kT, and therefore the dipolar polarizability, which is the um, dipole moment per electric field, that is P square by 3 kT. So if alpha 0 denotes the sum of the electronic and ionic polarizabilities, then uh, total polarizability may be written as alpha equals to alpha naught plus P square upon 3 kT. So this is the well-known Langevin-Debye equation and is of great importance to chemists in interpreting the molecular structures. So depending upon this equation, many numerical problems may be solved. Maybe in the next assignment, I will give this assignment on dielectric properties of materials, but this is the most important equation in understanding the molecular structures, right? So again, I am discussing this at uh, 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 minimum understanding of the numerical values of these. Uh, we depend this the dipole moment P is determined either by alpha or the molar polarizability as a function of 1 upon T. So I am giving the plots in the little later, but okay. As I mentioned, the polarizability arising from the orientation of the electric field of molecules possessing a permanent electric dipole moment is usually discussed only with the reference to the gaseous and liquids, but it is of importance in other solids. So this type of polarization was first discovered by Debye, who showed that by assuming the molecules could have permanent dipole moments, one could explain the high dielectric constant of water, alcohol, and other similar liquids, and the temperature dependence of their dielectric constants. Mm, The problem is that the dielectric constant of water is that of the static dielectric constant is 81 at room temperature, whereas this one, this one 81 at room temperature. But whereas the dielectric constant at optical frequency, that is refractive index square, refractive index of water is 1.33, which turns out to be 1.77 only. So it is known that for the difference is caused chiefly by the orientational polarization, which is effective at low frequencies, but is damped out for wavelengths shorter than about 1 centimeter. So the characteristic temperature dependence of the orientational polarizability of CH3Cl as permanent electric dipole moment. Methane and CCl4 do not. So they behave like a linear behavior with 1 upon T dependence over the molar polarizability. Here the plot signifies the m upon rho epsilon minus 1 upon epsilon plus 1 equals to 4 pi by 3 L alpha, which is known as the polar polarizability for polar and non-polar substituted methane compounds in gaseous form. So in the absence of the thermal agitation and the interactions among themselves, molecules with permanent dipole moments would all line up completely on application of the arbitrary small electric field, so that the dielectric constant would be infinite from the Clausius-Mossetti equation. So actually the orienting tendency of the electric field is partly compensated by the thermal agitation, and in solids uh, and some liquids, the orientation is hindered by close range mutual interactions of the molecules. I repeat, this is a very important observation, as if in the absence of the thermal agitation, the interactions among themselves, molecules with permanent dipole moments would all line up completely on the application of the arbitrary small electric field, so that the dielectric constant would be infinite, which is a fallacy. So actually the orienting tendency of the electric field is partly compensated by the thermal agitation, and in solids and some liquids, the orientation is hindered by close range mutual interaction of the molecules. So if we discuss some range of the molecules or the functions, the okay, this is the plot of Langevin-Debye equation. This is almost like one. This is my function LA equals to quad hyperbolic A minus 1 upon A. This is A upon LA, right? So the slope is simply related to P. So in this way, one obtains, for example, following dipole moments of, if we consider the asymmetric molecule HCl, which is 1.03 into 10 to the power minus 18 ESU, and dipole moment of HBr 0.79 into 10 to the power minus 18 ESU, and Hi is 0.38 into 10 to the power minus 18 ESU, and also of water is equals to 1.87 into 10 to the power minus 18 ESU. So the moments are often expressed in Debye units, where the Debye unit is 10 to the power minus 18 ESU in of the order of the electronic charge times an interatomic distance. So this is all about orientational polarizability. Now, an important observation comes from the dielectric constant calculation from the Clausius-Mossetti equation. But although this equation holds fairly accurately for nonpolar substances, it fails completely in pure polar liquids or solids. So to see this failure, and we neglect the deformation polarizability, we obtain this dielectric constant turns out to be 1 plus 4 pi np square over 3k times t minus tc, where we have set tc is equals to 4 pi np square over 9K. The dielectric constant would really become infinite at t equals to Tc, right? So this becomes infinite at t equals to Tc. But rather than the saturation effects should enter and the substance should become spontaneously polarized or ferroelectric. Actually, ferroelectric behavior is at present unknown in dipolar substances, although it is found in crystals which are more or less ionic in binding. We will discuss later on ferroelectric and piezoelectric crystals. But the fact is that using the known dipole moment of 1.87 debye units, we may estimate that the critical temperature which would be expected for water, that is, if this dipole moment are being used in this equation, then this Tc turns out to be 1200 degree K. So, which is in striking contradiction of the fact that neither water or ice is ferroelectric. So, this is an important phenomena in dielectric polarizability, which is called the polarizability catastrophe. So, this is called a catastrophe because neither water or ice possess ferroelectricity. Onsager pointed out that the theoretical basis of the Lorentz field from which the catastrophe stems does not include the case of the permanent dipole moments, as here the moments are not in general all parallel, as assumed in the discussion of in terms of E2 and E3 in the first field of local electric field. Onsager has developed an approximate theory for polar substances. If the induced polarization is neglected, the Onsager model gives this epsilon is functionally 1/4 of 1 plus 3x plus 3 times 1 plus 2/3 x plus x squared to the power half, where x equals to 4 pi np square divided by 3kt. So it is easily seen from this expression, which is derived from an approximation condition, and an exact solution has not yet been obtained. So it may be noted that the internal interactions which favor one direction of mutual orientation of adjacent molecules over the opposite direction may also tend to eliminate the critical point displayed in the phenomena of dielectric, dielectric polarizability catastrophe, which is known as the hindered rotation. So a recapitulation of the total classes on orientational polarizability and Langevin-Debye function. So I have discussed, in case of orientational polarization, we have a material with a built-in dipoles that are independent of each other. That is, they can rotate freely in sharp contrast to ionic polarizability. The prime example is the liquid water, where every water molecule is a little dipole that can have any orientation with respect to other molecules. Moreover, the orientation changes all the time because the molecules moves. So orientational polarization for dielectric dipoles thus is pretty much limited to liquids, but we will encounter it in major way again in the magnetic dipoles. So two-dimensional piece of water below one particular moment in time, it is like a snapshot to very short exposure time. A few nanoseconds later, the same piece of water may look totally different in detail, but the pretty much the same in general. So in a three-dimensional piece of water, the uh, easy to imagine and difficult to draw. So the dipoles are not sitting still, but moving around in rotation all the time because they contain thermal energy and thus the sum of entropy. So whenever two molecules collide, the new orientation is random. All memory of the orientation that they might have had in the electrical field is lost. So this is analogous to what happens to electrons carrying an electrical current in an electric field. So ultimately, uh, we have used the equation of Debye equation, sorry, Langevin equation and Langevin-Debye equation. We have derived the Langevin function. I must mention one plot here, which is very much important to remember for physics honor students. What are the functional dependence of cot hyperbolic x? Not the Langevin equation, but how cot hyperbolic x varies, right? So this is my axis. So cot hyperbolic x basically this type of asymptotic behaviors, right? This is x, this is y. We have plotted y equals to cot hyperbolic x, which is the hyperbolic cotangent defined as e to the power x plus e to the power minus x upon e to the power x minus e to the power minus x. That is 1 upon tan hyperbolic x. And the behavior of this, the Langevin equation, so called, okay. So this is the asymptotic value, and this is definite result, but it does not help much. We need to discuss the mathematical construction of Langevin function to get some idea of what we have obtained. So two water molecules coming in close contact will of course feel each other, and they may have preferred orientations of their dipole moments relative to each other. So in this case, we will have to modify the calculations, and the above equations may no longer be a good approximation. So on the other hand, if there is a strong interaction, we automatically have some bonding and obtain a solid ice in case of water. The dipoles most likely cannot orient themselves freely. We have a different situation, usually ionic polarization. There are, however, some solids where dipoles exist that can rotate to some extent. We will get very special effects that is called ferroelectricity. So this is all about orientational polarization. I have mentioned almost all things. So I end this class here.